Imagine a wooden vessel so revolutionary that it changed the entire course of human history. A ship that could survive months at sea, navigate uncharted waters, and carry explorers to lands no European had ever seen. In the 15th and 16th centuries, while most of Europe was still building coastal vessels, Portuguese shipwrights were crafting maritime masterpieces that would discover new continents, establish global trade routes, and create the first true world empire. These weren't just boats, they were floating fortresses, scientific laboratories, and gateways to the unknown. Today, I'm taking you inside the shipyards of medieval Portugal to reveal exactly how these legendary vessels were built, from the first cut of timber to the moment they touched water. Before we set sail on this journey, hit that subscribe button and smash the like if you're fascinated by history and engineering. Trust me, you won't want to miss what's coming next. To understand how Portuguese ships were built, I need to first take you back to early 15th century Portugal. This was a small kingdom on the western edge of Europe, pressed against the Atlantic Ocean with Spain as its only neighbor. The Portuguese had limited resources, a small population, and were essentially blocked from expanding eastward into the Mediterranean by more powerful kingdoms. But what they did have was an extensive coastline, a proud maritime tradition, and a visionary leader named Prince Henry the Navigator. Prince Henry, despite his nickname, wasn't actually a navigator himself. He never commanded a ship on a voyage of discovery. But what he did was perhaps even more important. He created the world's first organized program of maritime exploration and shipbuilding innovation. Around 1419, Henry established a sort of maritime research center at Sagres on Portugal's southwestern tip. Here, he gathered the best cartographers, astronomers, shipwrights, and sailors he could find from across Europe and the Mediterranean world. The strategic vision was clear. If Portugal couldn't expand on land, it would expand by sea. But this required ships unlike anything Europe had seen before. You see, the ships of northern Europe, the cogs and hulks, were excellent for cargo transport in the relatively calm Baltic and North Seas. The ships of the Mediterranean, galleys powered by oars and triangular lateen sails, worked wonderfully in those enclosed, predictable waters, but neither design could handle what the Portuguese needed to do: sail far out into the open Atlantic, navigate along the treacherous African coast with its contrary winds and currents, and return home again. I find it fascinating that the Portuguese approach to this challenge wasn't to reject existing designs entirely, but to synthesize the best elements from multiple maritime traditions. They looked at the sturdy hull construction of northern European ships. They studied the lateen sails of Arab vessels that could sail closer to the wind. They examined the steering mechanisms of various Mediterranean craft. And then, in their shipyards along the Tagus River and in cities like Porto and Lagos, they began experimenting, combining and innovating. This wasn't just about building better ships, it was about building ships for a specific purpose. Portuguese vessels needed to be relatively small and maneuverable to explore coastal waters and river mouths. They needed to be able to sail against the wind to return from their southern explorations. They needed to be sturdy enough to survive Atlantic storms, but shallow enough to beach for repairs. They needed to carry enough supplies for months at sea, but remain fast enough to outrun pirates or hostile vessels. The shipbuilding program that emerged from this vision was systematic and well-funded. The Portuguese crown invested heavily in shipyards, subsidized timber acquisition, and maintained a corps of skilled shipwrights. Records from the period show that the Arsenal Real in Lisbon became one of Europe's most advanced shipbuilding facilities, employing hundreds of workers and producing dozens of vessels each year at its peak. What impresses me most about this strategic vision is how it combined practical maritime needs with cutting-edge scientific knowledge. Prince Henry's centre brought together pilots who could share their experiential knowledge of winds and currents with mathematicians who could calculate latitudes and chart courses. This marriage of practical craftsmanship and theoretical knowledge created an environment where shipbuilding could evolve rapidly. By the 1430s, this vision was already bearing fruit. Portuguese vessels were pushing farther down the African coast than any European ships had ventured before. Each voyage brought back knowledge that would be incorporated into the next generation of ships. The shipwrights of Portugal weren't just building vessels. They were engaged in an iterative process of design, testing, and refinement that would continue for over a century. Now let me introduce you to the ship that became synonymous with Portuguese exploration, the caravel. If you've heard of Christopher Columbus, Vasco da Gama, or Ferdinand Magellan, you've heard of their ships, and many of those were caravels. This vessel type was Portugal's greatest maritime innovation, and understanding how it was built requires understanding what made it so special. The caravel emerged in the 1430s, though its exact origins remain debated by historians. What we do know is that it represented a radical departure from existing ship designs. A typical caravel was relatively small, usually between 50 to 70 feet in length, with a narrow hull and a shallow draft. But its defining feature was its sail plan. Early caravels used what's called a lateen rig, triangular sails mounted on long yards attached to the mast at an angle. This wasn't a Portuguese invention. Arab sailors had been using lateen sails for centuries in the Indian Ocean and Mediterranean. But the Portuguese were the first to successfully adapt this sail plan to Atlantic conditions and combine it with European hull construction techniques. Why does this matter? Because lateen sails allowed a ship to sail much closer to the wind, meaning they could make progress even when the wind was coming from ahead at an angle, not just from behind. For the Portuguese exploring down the African coast, this was crucial. They could sail south with the prevailing northerly winds, but more importantly, they could sail back north against those same winds. Earlier ships could only sail downwind, which meant returning from southern explorations required either waiting months for seasonal wind changes or rowing, neither practical for long-distance voyaging. Let me describe a typical caravel's specifications to give you a clearer picture. The hull would be built using a technique called carvel planking. Despite the similar name, this actually refers to the construction method, where planks are laid edge to edge on a frame, creating a smooth outer surface. This contrasted with the clinker or overlapping plank method common in Northern Europe. The caravel planking technique created less water resistance, making the ship faster and more efficient. The caravel typically had 2 or 3 masts. The main mast in the center would be the tallest, perhaps 50 to 60 feet high. The foremast toward the bow would be somewhat shorter, and if there was a third mast, the mizzen at the stern, it would be shorter still. Each mast could carry 1 or 2 lateen sails, giving the ship tremendous flexibility in handling different wind conditions. The hull shape was particularly clever. The caravel had a relatively flat bottom compared to other ships of the era, which gave it a shallow draft, sometimes as little as 6 feet. This meant caravels could navigate close to shore, enter shallow harbors, and even be beached for repairs if necessary. Yet despite this shallow draft, the hull shape was designed to minimize leeway, the tendency of a ship to drift sideways when sailing at an angle to the wind. Inside, the caravel was surprisingly spacious for its size. There would typically be a small raised deck at the stern, called the quarterdeck, where the captain and helmsman would work. Below the main deck, the hull would be divided into sections for cargo, provisions, and sometimes minimal crew quarters, though many sailors would sleep on deck in good weather. One of the most ingenious aspects of caravel design was its adaptability. Shipwrights discovered they could easily modify the rig depending on the voyage's needs. For exploration along coasts, the lateen rig was perfect. But for long ocean crossings with favorable following winds, crews could switch to square sails, rectangular sails that hung perpendicular to the ship's centerline. These were more efficient for downwind sailing and easier to handle with small crews. This hybrid version became known as the caravella redonda, or round caravel, as opposed to the pure lateen-rigged caravella latina. The caravel's size was also strategic. A ship this small required a crew of only about 20 to 30 men, compared to 50 or more for larger vessels. This meant lower costs for wages and provisions, crucial for speculative exploration voyages that might not yield immediate returns. It also meant less food and water needed on board, extending the ship's range. But perhaps the most important feature of the caravel was one you couldn't see. It was relatively easy and quick to build. While a large galleon might take 2 years or more to construct, an experienced crew could build a caravel in 6 to 8 months. This meant Portugal could quickly build fleets of exploration vessels, and losses at sea, which were common, could be replaced relatively quickly. I should mention that caravels weren't perfect. They were cramped and uncomfortable for long voyages. They couldn't carry much cargo, which limited their usefulness for trade once routes were established. They weren't particularly good in combat against larger warships. But for their intended purpose, exploring unknown waters and establishing initial contact with distant lands, they were absolutely unmatched. The proof is in the history. The ships that rounded Cape Bojador in 1434, breaking through a psychological barrier that had stopped European sailors for decades, were caravels. The ships that explored the West African coast reached the Cape of Good Hope, and eventually sailed to India, were caravels. 2 of Columbus's 3 ships on his first voyage to the Americas, the Niña and the Pinta, were caravels. These vessels opened the world to European exploration, and they were a uniquely Portuguese creation. Now let's get into the actual construction process, and it all starts in the forest, not the shipyard. Building a ship in the 15th or 16th century was an incredibly resource-intensive undertaking, and by far the most important resource was timber. A single caravel might require 200 to 300 mature trees. A large carrack or galleon could require over 1,000. And not just any trees would do. Shipwrights needed specific types of wood with particular characteristics for different parts of the vessel. The Portuguese were fortunate to have access to excellent timber resources, both domestically and through their trading networks. The primary wood for ship construction was oak, specifically Portuguese oak and cork oak from the forests of central and northern Portugal. Oak was prized for its strength, durability, and natural resistance to rot. The keel, the ship's backbone running along the bottom from bow to stern, had to be oak, as did the main structural ribs that gave the hull its shape. But a ship required many different types of wood. Pine was used for planking and decking because it was lighter than oak and easier to work with. Masts were typically made from pine or fir, which provided the necessary combination of strength and flexibility. A mast needed to bend in the wind without breaking. For specialized components like pulleys and deadeyes, shipwrights preferred hardwoods like walnut or cherry. Cork was used for buoys and sometimes for insulation in holds where delicate cargo would be stored. The process of selecting timber was taken very seriously. Master shipwrights or their experienced deputies would personally visit forests to mark trees for felling. They weren't just looking at the size of the tree, they were reading its grain, assessing how the wood fibers ran, identifying natural curves that could be used for specific ship components. A naturally curved tree trunk might be perfect for a knee, the L-shaped brackets that connected the ship's ribs to the deck beams. Using naturally curved wood was far stronger than trying to bend straight timber or cutting curves across the grain. Timing was crucial. Trees were typically felled in late fall or winter when the sap was down and the wood contained less moisture. This made the timber less prone to cracking and warping as it dried. The felling itself was done with axes and two-man crosscut saws, backbreaking work that required skill to bring a massive tree down safely and in the right direction. Once felled, the real work began. Green timber, freshly cut wood, was far too unstable to use immediately. It needed to be seasoned, a process that could take months or even years, depending on the thickness of the timber and local conditions. The Portuguese used several seasoning methods. Sometimes timber would be left in the forest for weeks to begin the drying process before transportation. Other times, logs would be partially submerged in water, typically salt water or brackish estuaries, for several months. This water seasoning leached out sap and some of the wood's natural sugars, making it more resistant to marine borers and rot. After water seasoning, timber would be stacked in covered but well-ventilated storage areas at the shipyard, carefully spaced so air could circulate around each piece. The stacks would be oriented to prevent direct sunlight from causing uneven drying. Weights might be placed on top to prevent warping. The general rule was that wood needed to season for about 1 year per inch of thickness, though in practice, demand often meant timber was used before it was fully seasoned. Transportation of timber was itself a major undertaking. Logs from inland forests had to be dragged by oxen to rivers, where they could be floated downstream to the coast. Large timber suitable for keels or masts was especially challenging to transport. These might be 60 feet long and weigh several tons. Coastal forests had an obvious advantage, which is why areas near Porto and along the Tagus River became centers of Portuguese shipbuilding. Once at the shipyard, timber had to be converted from round logs into useful shapes. This was done in saw pits, long trenches where one sawyer stood below and another above, working a long two-man saw to rip logs lengthwise into planks and beams. This was exhausting work. Experienced pit sawyers could cut perhaps 100 feet of board length in a day. The man in the pit below had the worst of it, working in cramped conditions filled with sawdust. The Portuguese also imported specialty timbers when needed. Cedar from North Africa was prized for its natural oils that resisted rot and pests. Exotic hardwoods from Brazil and Africa would later be incorporated into Portuguese ships. As Portugal's empire expanded, the empire's forests essentially became the shipbuilder's supply depot. One aspect of timber selection that fascinates me is how much practical knowledge was required. Master shipwrights could look at a log and predict how it would behave, where it might split, how much it would shrink, whether its grain pattern would make it strong or weak in particular applications. This knowledge was passed down through apprenticeship. There were no textbooks or engineering manuals. A shipwright's education was years of working with wood, learning to read it like a language. By the time timber arrived at the shipyard, properly selected, seasoned and prepared, a significant investment had already been made in time, labor and capital. But this careful preparation was essential. Use poor timber or timber that wasn't properly seasoned, and your ship might last only a few years instead of decades. The Portuguese understood that their exploration program required ships that could survive multiple voyages, and that started with the finest timber available. Now let's talk about the people who actually built these ships, because medieval shipbuilding was a highly organized craft industry with clear hierarchies, specialized roles, and jealously guarded knowledge. At the top of this hierarchy stood the master shipwright, the mestre carpinteiro in Portuguese, and understanding his role is key to understanding how these ships came together. The master shipwright was part engineer, part artist, and part project manager. He was responsible for the entire design and construction of the vessel. But here's what's remarkable. He did this almost entirely without written plans or detailed drawings. There were no blueprints in the modern sense. Instead, the master shipwright carried the ship's design in his head, supplemented by a few basic measurements and proportions that might be sketched on a board or marked on the shipyard floor. This design method was based on a system of proportions and rules of thumb that had been developed over centuries. The master shipwright would start with a fundamental measurement, typically the keel length, and all other dimensions would be calculated as ratios of that measurement. The beam, the ship's width, might be 1/3 of the keel length. The depth of the hold might be half the beam. The height of the mainmast might be twice the keel length plus 1/3. These weren't arbitrary ratios. They were the accumulated wisdom of generations of shipbuilders, refined through trial and error. The master shipwright's knowledge was considered extremely valuable, almost secret. These craftsmen commanded high salaries and were recruited actively by competing nations. There are records of the Spanish and English trying to lure Portuguese master shipwrights away with promises of titles and estates. Some Portuguese shipwrights did emigrate and built ships for other nations, taking Portuguese techniques with them, which is partly how caravel-style designs spread across Europe. Under the master shipwright was a hierarchical team of specialized craftsmen. The caliphate, or caulker, was responsible for sealing the gaps between planks with oakum, fibers from old rope mixed with tar, to make the hull watertight. This was skilled work. Poor caulking could doom a ship. The ferrero, or smith, forged the thousands of nails, bolts, and iron fittings needed. Ship nails were specially designed with square shanks that twisted as they were driven into the wood, creating a stronger hold than round nails. Carpenters of various specializations made up the bulk of the workforce. There were roughing carpenters who did the initial heavy cutting and shaping. Finish carpenters did the more precise work on deck fittings and interior spaces. Specialist carvers might create decorative elements for the stern, castle, or bow. Each of these craftsmen had served years as apprentices learning their trade. The sawyers we discussed earlier were also crucial team members, constantly converting stored timber into the specific shapes and sizes needed. Riggers would handle the complex web of ropes that controlled the sails. Sailmakers, often a separate trade guild, would cut and sew the massive sheets of canvas. Painters would apply protective coatings and decorative elements. A typical shipbuilding project might employ 50 to 100 men directly, with many more working in supporting roles, making rope, weaving canvas, producing tar and pitch, forging metal fittings. The Royal Arsenal in Lisbon, at its peak, employed over 300 people directly and provided work for thousands more in related industries. The construction schedule was carefully organized. Different crafts would work on the ship in sequence, though there was significant overlap. The initial framing might take 2 to 3 months. Planking could take another 2 months. Caulking, fitting the deck, stepping the masts, and rigging might take 2 more months. Then there was finishing work, painting and loading provisions and ballast. Throughout this process, the master shipwright was constantly present, checking proportions, solving problems, and adjusting the design as needed, based on how the actual timber was behaving. What strikes me most about this system is how it balanced standardization with flexibility. The proportional system meant that ships of a given type had consistent characteristics. All caravels shared certain features that made them recognizable and predictable. But the master shipwright had tremendous latitude to adapt designs to specific needs, available materials, or lessons learned from previous vessels. This wasn't mass production, but it wasn't purely custom work either. It was something in between, a craft tradition with enough consistency to build ships reliably, but enough flexibility to keep improving. The social status of shipwrights was interesting too. In medieval Portuguese society, they were considered skilled craftsmen, a step above common laborers, but below merchants and nobility. Yet master shipwrights could accumulate significant wealth and respect. Records show some receiving land grants, tax exemptions, and honors from the crown in recognition of their service. Their work was understood to be essential to Portugal's maritime expansion, and therefore to national interests. Training the next generation was formalized through the apprenticeship system. A boy might enter a shipyard as young as 12 or 13, starting with menial tasks like carrying tools and cleaning up. Gradually, he would be given more responsibility, learning to handle tools, understand timber, and master specific techniques. After 7 to 10 years, he might become a journeyman carpenter, working independently but under supervision. Only after many more years, and demonstrating exceptional skill and knowledge, might he become a master shipwright himself. This system ensured that knowledge was preserved and passed down, but it also meant that innovation happened gradually. A young apprentice in the 1440s might become a master shipwright in the 1460s, building ships largely the way his master had taught him, with only incremental improvements. Yet over decades, these incremental improvements accumulated into significant advances. The caravels of 1450 were noticeably better than those of 1420, and the carracks of 1500 were more sophisticated still. Let me walk you through the actual construction process step by step, because this is where Portuguese innovations really shone. The building of a ship began long before the first timber was laid. It started with preparing the construction site and establishing the vessel's fundamental geometry. The shipyard itself was carefully chosen and prepared. Ideally, it would be on a gentle slope leading down to the water, with the ship built on a slipway, an inclined plane of timber rails greased with tallow. This would allow the finished vessel to slide into the water during launching. The ground needed to be firm enough to support the enormous weight of the ship under construction, but accessible to the water for the eventual launch. The first physical step was laying the keel. Remember, the keel is the ship's backbone, running from bow to stern along the bottom center. For a caravel, this might be a single massive oak timber 50 or 60 feet long, perhaps 12 inches square in cross-section. The keel had to be perfectly straight and level. This was checked meticulously with plumb lines and leveling boards. The keel was blocked up on sturdy supports, positioned precisely according to the master shipwright's specifications. At each end of the keel, vertical or steeply angled timbers were attached, the stem at the bow and the stern post at the stern. These weren't simple joints. They were complex, interlocking connections, often reinforced with iron bolts, and sometimes featuring intricate scarf joints where multiple timbers were joined end to end. The Portuguese used what's called a hooked scarf joint, or keyed joint, where stepped or notched surfaces locked together, providing enormous strength. Now came something absolutely crucial to Portuguese shipbuilding: establishing the hull shape. This is where the master shipwright's expertise was most vital. Using the proportional system I mentioned earlier, he would determine the location and shape of the main frames, the U-shaped or V-shaped ribs that would define the hull's cross-sectional shape at various points along its length. The Portuguese used a frame-first or skeleton-first construction method. They would erect the keel, stem, and stern post, then install the main frames before applying the outer planking. This was in contrast to some earlier shipbuilding traditions that built the outer shell first and then inserted framing inside. The frame-first method allowed for stronger, more consistent hull shapes and was one of the key innovations that made Portuguese ships so durable. The frames were massive curved timbers, often made from naturally curved trees or assembled from multiple pieces joined together. Each frame would be temporarily braced to hold its exact position and angle. The master shipwright would move along the keel, ensuring each frame was positioned correctly and that the overall hull shape was smooth and fair. This was done by eye and experience. He could sight along the frames and see if the curves were consistent, if there were any irregularities that would cause problems. Between the main frames, lighter frames called futtocks would be installed, creating a complete skeleton of curved ribs along the entire length of the hull. Inside this framework, longitudinal timbers called stringers or wales would be attached. running parallel to the keel and connecting the frames together, adding tremendous stiffness to the structure. Then came the planking, attaching the outer skin to this skeleton. This is where the Carvel planking technique showed its advantages. The planks were carefully shaped to fit edge to edge, creating a smooth outer surface. This wasn't simply a matter of nailing boards to the frames. Each plank had to be shaped precisely to match the compound curves of the hull. The planking process was methodical and started from the keel upward. The first plank on each side, called the garboard strake, connected directly to the keel and had to fit perfectly. Each subsequent plank, called a strake, had to align precisely with the one below it. The Portuguese shipwrights used hot water or steam to make the planks more pliable when bending them to match the hull's curves. Planks were held in place with a combination of iron nails and wooden pegs called tree nails, pronounced trunnels. Here's a detail that shows the sophistication of Portuguese technique. They didn't just nail planks randomly. There was a specific pattern to fastening the distributed stress evenly. The planks were also beveled along their edges, so they would fit tightly together, and the thickness of the planking varied, thicker and stronger near the waterline where strain was greatest, somewhat thinner, higher up to save weight. As the planking reached the waterline, extra care was taken. This area would face the most stress from waves and water pressure. The Portuguese often used thicker planks here and might install additional internal reinforcement. Below the waterline, planks were sometimes doubled, 2 layers for extra strength and protection. Once the outer hull was planked, the caulkers took over. They would hammer oakum into every seam between planks using special iron tools and wooden mallets. The oakum would be packed in tightly, compressing into the gap, then sealed over with hot pine tar or pitch. Done properly, this created a waterproof seal that would last for years. The rhythmic sound of caulking mallets was a constant soundtrack in any working shipyard. The deck came next. Deck beams, heavy transverse timbers, were installed, resting on the ship's side frames and sometimes supported by posts or pillars in the center. Deck planks would be laid across these beams. The deck had to be slightly crowned, higher in the center than at the sides, so water would run off rather than pooling. The Portuguese made innovations in deck layout too. They developed the raised quarterdeck at the stern, providing a commanding position for navigation and ship handling. Later designs added a raised forecastle at the bow. These elevated platforms had military applications. They were ideal positions for archers or later for small cannons, but they also improved the ship's handling by moving weight toward the ends. Interior spaces were fitted out based on the ship's purpose. Cargo holds would have hatches and sometimes removable bulkheads. Water casks and food storage would be positioned for best weight distribution. On military vessels, gun ports might be cut in the hull sides with hinged covers that could be sealed in rough weather. Now came stepping the masts, installing them in their permanent positions. The main mast was the most challenging. Its base, called the mast step, was a reinforced socket in the keelson, a heavy timber that ran above and parallel to the keel. The mast itself, perhaps 50 feet tall and 2 feet in diameter at the base, had to be lifted upright and lowered precisely into this step. This required coordinated effort from dozens of workers using pulleys, ropes, and sheer legs, temporary wooden frames that provided mechanical advantage. Once stepped, the mast was secured with wedges in the mast step and additional support from deck partners, reinforced openings where the mast passed through the deck. The foremast and mizzenmast, if present, would be stepped similarly, but were generally smaller and somewhat easier to install. The rigging came last, the complex web of ropes that controlled the sails and supported the masts. Standing rigging, the permanent lines that held the masts steady, was set up first. This included shrouds running from the masthead down to the hull sides and stays running forward from each mast. These weren't just simple ropes. They were carefully tensioned and included ingenious tensioning devices called deadeyes and lanyards that could be adjusted to tune the mast's support precisely. Running rigging, the lines used to raise, lower and control the sails, was tremendously complex. A single mast might have dozens of lines, each with a specific purpose. Halyards to raise and lower sails, sheets to control the angle of the sail, braces to rotate the yards that held the sails. Everything had to be organized so sailors could find the right line quickly, even in darkness or storm conditions. What amazes me about all of this is the precision achieved without modern tools. No power tools, no computer-aided design, no laser levels or precise measuring instruments, just skilled craftsmen with hand tools, geometric knowledge, and generations of accumulated experience. Yet the results were ships that could cross oceans and return, that could survive storms, that would destroy lesser vessels, that were efficient enough to make long-distance trade economically viable. The Portuguese construction techniques would gradually spread across Europe as their shipwrights traveled or shared knowledge, and as other nations captured or purchased Portuguese-built ships to study. But for several crucial decades in the 15th century, Portuguese shipyards represented the cutting edge of maritime technology, and the techniques developed there would influence ship construction for the next 400 years. With the hull complete and the masts stepped, a ship was still far from ready to sail. The rigging and sails transformed a wooden structure into a functioning vessel, and this is where we see more Portuguese innovation. Let me take you through these crucial systems that made exploration possible. The sail plan of a Portuguese caravel was its defining feature. As I mentioned earlier, the classic caravel latina used triangular lateen sails. These sails were massive triangles of canvas, their top edge attached to a long yard, a wooden pole that was hung from the mast at an angle. A typical mainmast lateen sail might be 40 feet along its longest edge, containing hundreds of square feet of canvas. Making these sails was specialized work. Sailmakers would start with bolts of canvas, heavy fabric woven from hemp or flax. Canvas came in different weights. Portuguese sailmakers used heavier canvas for lower sails that faced more wind pressure, lighter canvas for higher sails. The canvas would be cut in panels and sewn together with remarkably strong hand-stitching, creating seams that could withstand tremendous strain. The edges of the sail were reinforced with rope, sewn into a pocket along the edge, a technique called bolt roping. Corner patches were added where the most stress would concentrate. Reef points, short lines sewn through the sail at intervals, allowed sailors to reduce sail area in heavy winds by tying up a portion of the sail. These weren't just practical additions, they were carefully engineered features based on understanding how sails failed under stress. The lateen rig's genius was in how it could be trimmed, adjusted to make best use of the wind. When sailing at an angle to the wind, the sail would be set so the wind flowed across its surface, creating lift much like an airplane wing. The long yard could be rotated around the mast, allowing the sail to be positioned optimally for almost any wind direction except directly ahead. But lateen rigs had disadvantages too. The long yard made the sail difficult to handle, especially when tacking, changing course to sail to the other side of the wind direction. The entire yard had to be repositioned to the other side of the mast, a complex maneuver requiring coordinated action by the crew. In storms, lateen sails were challenging to reef or lower quickly. This is why the Portuguese developed the caravela redonda, the round caravel, which mixed square sails on the foremast and mainmast with a lateen sail on the mizzenmast. Square sails were much simpler to handle for downwind sailing. They were hung from yards that were perpendicular to the mast and could be raised, lowered and reefed more easily. The combination gave captains options. Use the lateen rig when working along a coast or sailing into the wind. Shift to square sails for long ocean passages with favorable winds. Now let's talk about the navigation systems. because finding your way across thousands of miles of open ocean with no landmarks is perhaps humanity's most impressive early technical achievement. Portuguese navigators combined multiple methods and instruments to determine their position and course. The magnetic compass had reached Europe from China by the 13th century, but Portuguese navigators refined its use. The compass they used was typically a magnetized needle balanced on a pivot, mounted in a wooden box with a compass card showing the cardinal directions. This was kept in a binnacle, a stand near the helmsman that protected the compass from weather and kept it level despite the ship's motion. The compass provided direction relative to magnetic north, which wasn't quite the same as true north, but experienced pilots knew how to account for this variation in different parts of the ocean. For measuring latitude, north-south position, Portuguese navigators used several instruments. The astrolabe, adapted from astronomical instruments used by Arab and Jewish scholars, could measure the angle of the sun or North Star above the horizon. From this angle, with the help of tables showing the sun's position throughout the year, a skilled navigator could calculate latitude with reasonable accuracy. The Portuguese also developed the mariner's astrolabe specifically for use at sea. Unlike the ornate astronomical astrolabes used on land, the mariner's version was simpler, heavier, and had cutouts in its face to reduce wind resistance. It was usually made of brass or bronze, circular, with a rotating sighting bar called an alidade. A navigator would hang the astrolabe vertically, sight the sun or star through the alidade's pinholes, and read the angle off a scale engraved on the rim. Another instrument that became popular was the quadrant, a quarter circle of wood or metal with a plumb line hanging from its center point. By sighting along one edge at a celestial body and letting the plumb line settle, the navigator could read the angle on a scale. It was simpler than an astrolabe, but less accurate in rough seas. Later, the crossstaff was developed, a long stick with a sliding crosspiece. The navigator would hold one end to his eye, slide the crosspiece until it spanned the distance between the horizon and a celestial body, then read the angle from markings on the staff. This was easier to use than an astrolabe in many conditions, but here's what's crucial to understand. These instruments only gave latitude, how far north or south you were. Determining longitude, how far east or west, was nearly impossible with 15th and 16th century technology. Accurate longitude determination requires precise timekeeping, and mechanical clocks that could keep accurate time aboard a rocking ship wouldn't be invented until the 18th century. So how did Portuguese navigators find their way east and west? They used a technique called dead reckoning. The navigator would estimate the ship's speed by throwing a piece of wood overboard at the bow and timing how long it took to reach the stern, or later by using a chip log, a piece of wood on a knotted rope that was thrown overboard while someone counted knots as the rope played out. Combined with compass direction and estimated time, the navigator could calculate approximately how far the ship had traveled in any direction. This required maintaining a detailed logbook where every course change, estimated speed and distance traveled was meticulously recorded. Good navigators would also note currents, wind conditions, and any landmarks sighted. Over a long voyage, small errors in dead reckoning could accumulate into major positional uncertainty, which is why experienced pilots were so valuable. They could recognize landmarks, watercolor changes, bird species, and other clues to verify position. The Portuguese also developed navigational charts called portolan charts, which showed coastlines, ports, compass roses, and rhumb lines, straight-line courses between locations. These charts were valuable state secrets. The Casa da India in Lisbon maintained the official charts, updated them with information from returning voyages, and controlled their distribution. Captured charts from Portuguese ships were prized by competing nations. What impresses me most about Portuguese navigation was how it combined practical seamanship with emerging scientific knowledge. Navigators needed to be mathematicians who could use trigonometry tables to calculate latitude. They needed to be astronomers who understood celestial motion. They needed to be craftsmen who could maintain and calibrate delicate instruments. And they needed to be experienced sailors who could read weather, seas, and currents. This combination of skills was rare and made Portuguese pilots highly sought after. The navigation equipment was stored carefully aboard ship. Instruments were kept in the captain's cabin or a dedicated chart room, protected from salt spray and damage. Charts were stored flat in chests. Navigational tables and almanacs, books showing celestial positions throughout the year, were among a ship's most valuable possessions. Sand glasses, hourglasses filled with sand, were used to measure time, with a ship's boy responsible for turning them and ringing a bell to mark each half hour. After months of construction, the ship was finally complete, but it still faced crucial tests before it could be considered ready for service. Let me walk you through the final stages that transformed a construction project into a seagoing vessel. The first major milestone was the launch, getting the ship from the slipway into the water. This was both a technical challenge and a ceremonial occasion. The launch had to be timed with the tides, as you wanted high water to float the ship, but also needed enough time to complete the launch before the tide went out again. Days before the launch, workers would inspect the slipway carefully, adding additional grease to the rails. The blocks supporting the ship's weight would be adjusted so the vessel rested entirely on the slipway rails, not on any side supports. Heavy ropes would be attached to the ship, some to control its descent, others to pull it if needed. The launch ceremony itself was significant. A priest would bless the vessel, asking for divine protection for the ship and its future crews. The owner or sponsor might give a speech. Wine might be poured over the bow, the precursor to today's champagne bottle breaking. This wasn't just superstition, it was recognizing the danger that sailors would face and asking for their safe return. Then came the actual launch. Workers would knock away the final blocks holding the ship. If everything went perfectly, the ship's weight would start it sliding down the greased slipway, accelerating as it descended, then hitting the water with a tremendous splash. The hull would sink deep initially as its momentum carried it into the water, then bob back up as its buoyancy took over. Control ropes kept the ship from being carried away by current or wind, and small boats would move in to attach towing lines. Launches didn't always go smoothly. Sometimes ships would stick on the ways and refuse to move, requiring workers to dig under the keel or apply force with levers. Sometimes they would slide too fast, hitting the water so hard that they damaged the hull. There are records of ships rolling over during launch because their center of gravity was too high or the slipway was uneven. A successful launch was cause for celebration. Once afloat, the ship would be towed to a fitting-out wharf where the final work would be completed. Remember, the masts were already stepped, but much of the rigging wouldn't have been fully installed during construction. Now, with the ship floating and stable, riggers would complete their work, climbing the masts to install the upper portions of the standing rigging, running all the various lines through their appropriate blocks and securing them to their cleats and belaying pins. The ship would be ballasted, heavy material loaded into the bottom of the hold to lower the center of gravity and ensure stability. Ballast might be stones, sand, or even scrap iron. The amount and distribution of ballast was crucial. Too little, and the ship would be dangerously unstable. Too much, and it would sit too low in the water and be slow. The master shipwright and the ship's captain would work together to determine the proper ballast. Then came the first trials. The ship would be taken out into the harbor or nearby coastal waters with a minimal crew and no cargo. This was to test basic handling, how the ship responded to the helm, how it balanced under different sail configurations, whether it had any tendency to turn unexpectedly or sail sluggishly. Experienced captains could feel if something was wrong. A vibration, an unexpected movement, a sluggish response. If problems were found, the ship would return to the wharf for adjustments. Maybe ballast needed to be redistributed. Maybe a mast needed to be repositioned slightly. Maybe the rudder needed modification. These weren't failures, they were expected adjustments. No matter how experienced the master shipwright, each ship was unique and might need tuning. Sea trials would become progressively more demanding. The ship might be taken out in heavier weather to see how it handled. It would be sailed on different points of sail, downwind, crosswind, as close to upwind as possible, to verify performance. The crew would practice raising and lowering sails, tacking and wearing ship, dropping anchor. Any issues with rigging would become apparent. Lines might be repositioned, blocks might be moved, additional purchase might be added to make particular lines easier to handle. Once the ship passed its trials, it would be prepared for its maiden voyage. This was an exciting but also nervous time. For an exploration vessel, the maiden voyage might be into completely unknown waters. For a merchant ship, it would be a first trading journey with valuable cargo aboard. For a warship, it might be joining a fleet. Provisioning the ship was a massive undertaking. Food for weeks or months had to be loaded. Hardtack, a long-lasting dried biscuit that was the staple food, salted meat and fish, dried beans and peas, cheese, preserved fruits. Water was stored in large wooden casks. A ship might carry thousands of gallons. Wine or beer was actually preferred to water when possible, as it kept better, and the alcohol helped prevent illness. Other supplies had to be loaded too. Spare rope, spare canvas for sail repairs, barrels of tar and pitch, spare blocks and tools, weapons and ammunition if the ship might face combat, trading goods if it was a merchant voyage, scientific instruments for exploration vessels. Every cubic foot of space had to be used efficiently, with heavier items low in the hold for stability and frequently needed items accessible. The crew would come aboard, each man knowing his role and his station. A caravel might have 20 to 30 crew members, the captain who commanded overall, the pilot who navigated, the master who managed the crew and ship operations, several able seamen who worked the sails and lines, ordinary seamen still learning their craft, a cook, perhaps a carpenter for repairs, possibly a few soldiers or gentlemen adventurers if it was an exploration voyage. Life aboard these ships was harsh. Crew members would sleep wherever they could find space, on deck in good weather, in cramped spaces below deck in storms. There were no private areas except for the captain's cabin. Food was monotonous and often spoiled on long voyages. Water became stagnant. Rats were constant companions. Disease was common, especially scurvy, a vitamin C deficiency that Portuguese sailors wouldn't understand for centuries. Yet these men sailed anyway, driven by various motivations. Some sought adventure and glory, some hoped for wealth, as successful voyages could bring bonuses and opportunities. Some were driven by religious zeal, wanting to spread Christianity or battle Islam. Some were criminals or poor men with no other options. Together, they would man these remarkable ships and push the boundaries of the known world. The moment of departure was both thrilling and solemn. Final blessings would be given, last messages sent ashore, final supplies rushed aboard. Then the anchor would be raised, sails would be set, and the ship would begin its journey. The moment when the ship cleared the harbour mouth and met the open ocean was profound. Ahead lay the unknown. Behind lay safety. The ship that the Portuguese shipwrights had spent months building would now prove its worth. Now let me bring our journey full circle and talk about what all of this meant, not just for Portugal, but for world history. The ships we've been discussing weren't just remarkable pieces of engineering. They were instruments that fundamentally changed human civilization. The most obvious legacy is geographical. Portuguese ships sailing from Lisbon discovered and mapped huge portions of the earth that were completely unknown to Europeans. In 1415, Portuguese forces captured Ceuta in North Africa. This was really the beginning. Over the next century, Portuguese vessels would work their way down the African coast, each voyage pushing a bit farther south. Cape Bojador was passed in 1434. The Cape of Good Hope was rounded by Bartolomeu Dias in 1488. Vasco da Gama reached India in 1498, establishing the first direct sea route from Europe to Asia. Portuguese ships reached Brazil in 1500, likely by accident when a fleet bound for India swung too far west in the Atlantic. They reached China by 1513, Japan by 1543. By the mid-16th century, Portuguese vessels had visited almost every significant coastline in the world, from Newfoundland to Southeast Asia. The maps they created formed the basis for European geographical knowledge for centuries, but the impact went far beyond exploration. Portuguese ships established the first truly global trade network. Spices from India and Indonesia, silk from China, gold and ivory from Africa, sugar and Brazil wood from South America. Portuguese carracks and galleons carried these goods back to Europe in unprecedented quantities. The Casa da India in Lisbon became one of the world's great trading houses, processing goods from across the globe. This global trade network fundamentally altered European economies. Spices that had been worth their weight in gold became affordable to the middle class. New foods like sugar became dietary staples. The influx of wealth funded the Portuguese Golden Age, the Manueline architectural style, the University of Coimbra, patronage of explorers and scientists. It also funded competing nations' envy and eventually their own maritime expansion. The shipbuilding techniques developed in Portuguese yards spread across Europe. When Spain began its own maritime expansion, it relied heavily on Portuguese designs and often Portuguese shipwrights. The Spanish galleons that carried silver from the Americas back to Europe were descendants of Portuguese carracks. Dutch and English shipbuilders studied captured Portuguese vessels and incorporated their techniques. By 1600, every major European maritime nation was building ships influenced by Portuguese innovations. The caravel itself evolved into later ship types. The carrack, a larger, more cargo-capable vessel, was essentially an enlarged caravel with multiple decks and mixed sail plans. The galleon, which dominated the seas in the 16th and 17th centuries, owed much to Portuguese design principles. Even the great ships of the line that fought naval battles in the Age of Sail were distant descendants of Portuguese innovations in hull construction and sail plans. The navigation techniques pioneered by Portuguese pilots became standard practice worldwide. The charts they created, though initially guarded as state secrets, eventually became the foundation for later cartography. The instrumental techniques they refined, using astrolabes, quadrants, and later cross-staffs, remained standard until the 18th century. The concept of systematic exploration, where each voyage built on previous knowledge, became the model for all later exploration. There's a darker legacy too, one we can't ignore. Portuguese ships didn't just carry spices and explorers, they also carried enslaved people. The Atlantic slave trade, which would become one of history's greatest atrocities, began with Portuguese ships carrying enslaved Africans to Europe and later to American plantations. The same vessels that expanded human knowledge also enabled human exploitation on a massive scale. The colonial empires that Portugal and later other European nations established were made possible by these ships. The ability to project power across oceans, to supply distant outposts, to extract resources from far-flung colonies, all depended on reliable ocean-crossing vessels. The inequalities and conflicts created by colonialism still affect our world today, and those began with the ships we've been discussing. From a purely technical standpoint, Portuguese shipbuilding represented a remarkable synthesis of knowledge from multiple cultures. Arab sailing techniques, Northern European hull construction, Mediterranean navigation knowledge. Portuguese shipwrights took the best from each tradition and created something new. This kind of cross-cultural synthesis is often where the greatest innovations occur, and it reminds us that no culture innovates in isolation. The economic model that developed around Portuguese shipbuilding is also worth noting. The Portuguese crown invested heavily in maritime infrastructure, shipyards, timber supplies, training programs for pilots and shipwrights. This state-sponsored innovation program predated modern research and development by centuries. The returns on this investment were enormous, funding the Portuguese state for generations. The craftsmanship tradition is another legacy. The apprenticeship system, the trade guilds, the passing of knowledge from master to apprentice, these sustained quality and innovation over decades. In our modern world of rapid technological change, there's something to be learned from this slower, more deliberate approach to preserving and advancing technical knowledge. Today, you can still see Portuguese maritime heritage in museums around the world. The Museu de Marinha in Lisbon houses models and artifacts from the Age of Discovery. In Lagos, the Igreja de Santa Maria has a small maritime museum. Reconstructions of Portuguese ships have been built, including several caravels, allowing us to see these vessels under sail again. The techniques themselves haven't entirely disappeared either. Traditional wooden boat building still uses methods that would be recognizable to a 15th century Portuguese shipwright, selecting timber by grain, using naturally curved pieces, creating strong joints. The proportional design system, determining all measurements as ratios of a few key dimensions, is still used in some traditional boat building. Perhaps the most important legacy is inspirational. Portuguese ships proved that humans could cross oceans, could navigate unknown waters, could build vessels capable of surviving months at sea. This expanded the human sense of what was possible. It showed that careful planning, technical innovation and brave execution could overcome seemingly impossible challenges. Every space mission, every deep-sea exploration, every push into the unknown owes something to those Portuguese sailors who first showed that the horizon wasn't a limit, but an invitation. The wooden ships built in Portuguese yards in the 15th and 16th centuries were the culmination of centuries of maritime tradition and the beginning of a new era of global connection. They were triumphs of engineering, created by skilled craftsmen working with hand tools and accumulated knowledge. They were instruments of exploration that revealed the true size and shape of our world. They were vehicles of commerce that created the first global economy. And they were, for better and worse, the means by which European civilization spread across the globe. When you understand how these ships were built, the careful selection of timber, the generations of knowledge embedded in the master shipwright's mind, the months of labor by dozens of craftsmen, the innovative techniques and designs, you understand them not just as wooden vessels, but as achievements of human ingenuity. They represent what humans can accomplish when practical craft knowledge combines with scientific understanding, when innovation builds on tradition, when vision is backed by skill and determination. The Portuguese ships that sailed from Lisbon in the 15th and 16th centuries changed the world, not just politically or economically, but psychologically. They showed that the world was larger and stranger than anyone had imagined. They proved that human ingenuity could overcome natural barriers. They demonstrated that knowledge could be systematically accumulated and built upon, and they reminded us that sometimes the greatest achievements come from those willing to sail into the unknown. And that brings us to the end of our voyage through Portuguese shipbuilding history. If you enjoyed this deep dive into how these revolutionary vessels were constructed, make sure you hit that subscribe button so you don't miss our next historical adventure. I've got more incredible stories about maritime history, engineering marvels, and the explorers who changed our world. Drop a comment below telling me which aspect of Portuguese ships fascinated you the most. Was it the construction techniques that created such seaworthy vessels, the navigation systems that guided explorers across unknown oceans, Or maybe the incredible bravery of the sailors who trusted their lives to wooden ships. I read every single comment, and your feedback directly shapes the content I create. Also, let me know what historical engineering topic you'd like me to explore next. Ancient Roman aqueducts, Viking longships, medieval cathedrals. Your suggestions drive this channel forward. Thanks for joining me on this journey through history, and I'll see you in the next video. Fair winds and following seas.